Alrighty, so we're going to talk about bond enthalpies. So this is our last section that we want to talk about here. And so we can estimate the magnitude of a chemical reaction's enthalpy by using the amount of energy that is released or absorbed in each chemical bond. And so bond enthalpy is the enthalpy change, the delta H, for the breaking of bonds in 1 mole of a gaseous substance. And so this is a big deal. It's got to be in the gas vapor, okay? It's got to be a gas substance. So essentially we're looking at the amount of energy to break a molecule into its separate atoms and then to break that, then to add the molecule back together again, okay? Bond enthalpy is always a positive quantity because energy is required to break chemical bonds. Conversely, the energy is released when the bond forms between 2 gaseous atoms or molecule fragments. And so the greater the bond enthalpy, the stronger the bond, okay? So some average bond energies for you. And so there is a table that we will use. You will be provided this table if you have to do any of these problems on your test, and you will have to do some of these on your test. But here's a table that you will see. And so we can look up a single bond and say, oh, this is what it is. This is how much energy is released when we break that bond, and this is how much energy is needed to form this bond, okay? And so using this table, I'm going to write up another ugly looking expression because I have to. But the delta H of reaction using bond enthalpy method is going to be the sigma of the bond enthalpies bonds broken. So the enthalpies of bonds broken minus the enthalpy of bonds formed. Okay, so bonds broken, bonds formed, minus bonds formed. Now, something that I want to make sure that you're aware of is a picture is a good help. So a good molecular image will help you. Okay, so you want to make sure that you have a good image of the molecule so that you know exactly how many bonds are being broken so you can see it, because otherwise you just don't know. So some other considerations to look at. Essentially you're breaking apart every bond in the molecule and then you're reforming every molecule. So make a good diagram to make sure that you're not forgetting anything. Lots of people go off because they're forgetting bonds, and so you can't, if you're doing it this way, you can't forget bonds. You got to make sure that you're counting everything, okay? Count all the bonds that are the same, otherwise you will be off. And so if there's multiple carbon-carbon bonds, you got to make sure that you count all of those too. I would go so far as to indicate and draw and write and put a 1 or a 2 or a 3 and make sure that you're using them all so that you know. But yeah. And then on tests, I'm going to have a structural formula for you. So you're going to have a good diagram there to know exactly how much is broken and how much is changed, and we'll get you there, okay? So this is, you'll be provided this table, you'll be provided a good structural diagram, and that'll be really helpful. So, all right, last sample, here we go. This is the one we're going to do. I'm going to erase this because we don't need it anymore. So it's bonds broken minus bonds formed. So methane plus Cl2 forms methyl chloride and hydrogen chloride. So here we go. Methane is CH4, okay, plus Cl2 makes methyl chloride, which is H. So it'll be Cl, CH3, plus hydrogen chloride, HCl. Okay, so now that's just a molecule. That's, yeah, we need to balance this though. Okay, so here we go. So CH4, Cl2, Cl1. Okay, so chlorine, there's 2 chlorines, 1 carbon, 4 hydrogens, 3 hydrogens, 1 hydrogen. So it's actually balanced. Now to get a good image of what this looks like, carbon, hydrogen, 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 Cl2 looks like this. We're going to make chlorine, hydrogen, plus HCl. Okay, so here we go. Now how many bonds are going to break, how many bonds are going to form. So remember, delta H of the reaction is the summation of the bonds broken minus the summation of the bonds formed. Okay, so broken minus formed. So 1, 2, 3, 4. So I'm going to break. So my delta H of my reaction is going to equal, I have 4 carbon-hydrogen single bonds. Those are going to be what get broken, plus 1 chlorine-chlorine single bond. Okay, so that's the first thing. That's what gets broken. Now we're going to subtract from that. Here I have 1, 2, I have 3. I have 3 carbon-hydrogen single bonds plus 1 carbon-chlorine single bond plus 1 hydrogen-chlorine single bond. Okay, so that's how that's going to go. Now all we have to do is put our energy into these and then do the math on it, and that's going to do what it does for us. Okay, so delta H of reaction is going to be 4 times carbon-hydrogen single bond. I look on my table, a carbon-hydrogen single bond is 413 kilojoules. Plus 1 chlorine-chlorine single bond. I look on my table and I see that a chlorine-chlorine single bond is 242. So 1 times 242 minus 3 carbon-hydrogen bonds. So this is going to be 3 times 413 kilojoules plus 1 carbon-chlorine single bond. So carbon-chlorine is going to be 328. So 1 times 328 plus 1 times a hydrogen-chlorine bond, which is going to be 431. Okay, and so that's how all of that gets broken down. And so when we plug and chug and do 4 times 413, we're going to get 1600 something plus 242, that's going to be 1800 something minus 1200, 14, and another 4, like 18, and what, 19 something. So the delta H for this reaction is going to equal negative 104 kilojoules based on the bonds broken and the bonds formed. Now, this is an estimate. Okay, all of these delta H calculations are really just an estimate to figure out what we can do and what we can't do. But there they go. So that's how you would use bond enthalpies to estimate the delta H of a chemical reaction. So that's it. See ya.